Okay, welcome everyone to our workshop, Emerging Opportunities for Battery Research and Manufacturing. We thought that this place is a good excuse to talk about batteries, but APS being a destination, I believe, for battery research.
The destination.
The destination, yes. And so this is I hope everybody has the agenda. This is what we're gonna be looking at today. We're gonna start with Tanvir's talk, and then move on to Susan's talk. And the last speaker for this session is gonna be Jordi Cabana. And in the afternoon, we're gonna have some panel discussions. I wanted to just give you a short overview. Why do I believe that APS is the destination for, for battery research? It's very hard to put it in 5 slides because there is so many beamlines and so many amazing techniques that actually are super useful for battery research that trying to consolidate it into 1 or 2 slides is close to impossible. So I just put a summary of where the battery research is being done, and what makes this place unique is the unique support that we give to our users for sample preparation. In fact, over the last shutdown, the activities in the battery lab has been expanding. I was trying to accommodate more chemistries. So now we offer access to 4 different glove boxes and 1 glove box for solid state batteries. So it's a solvent-free glove box. I divorced sodium from lithium because some of the additives that people recently have been adding to lithium batteries were causing some issues for sodium. So we decided to separate those, and also for people who do some research for sulfur cathodes, we have a separate space for them so they don't ruin everybody else's experiments. And over the time, we actually collected more electrochemical equipment as well. And I provide support for all the users that come. And if they never done operandi experiments, I'm here to help them as well. Oops. Oh no. So just this is the overview, what kind of techniques might be applied where when you look at all the vast techniques that are available at APS. And it's really depending what kind of scientific question you have, where you want to go to where you should go. And even for simple techniques like X-ray diffraction, we do have multiple beamlines. And you really have to say exactly what question you're after, because some beamlines might be more appropriate than others. The things that I want to highlight is that with the APS upgrade, there's some techniques that are being more exciting for batteries, like XPCS technique with the improved coherence might be more applicable for batteries, and looking at the ionic mobility in the structures. We're hoping to get more access to tomography for especially industry relevant applications. And of course, what we also had before, things that have been brought into before the shutdown, like focusing for the high energy beams, gives us more opportunity to look at the samples in a different way. This slide I always put in the talks, and the whole point of this slide is to show people that it's not one solution that fits all. Depending what you're trying to do, you might have to tune your experiment, and depending on the technique that you're trying to use, it might be more suitable to use one cell or another, or one type of experimental procedure than the other. And we are here for you to help you figure out what you need to do. And this is just an overview based on diffraction, the simplest technique, what kind of angles you can look at for battery. And this is the simplest thing, right? So the top corner here is just operandi experiment of trying to look at the new material behavior, trying to figure out what is the mechanism of the reaction. Here in the left bottom corner, we are looking at the depth profiling. Some of the high energy beamlines actually allow us these days, if we use high enough flux and focused beam, we can actually use unmodified coin cells and look at the depth profiling of within those cells. So then we are not limited in the performance. We can use them at the operational conditions, and we have done this experiment even in fast charge modes. Because the data collection for some of those beamlines, we can't collect data within the 0.1 seconds, so that opens up the relevant timescales for that type of experiment. And on the right side, we are looking at mapping of the pouch electrodes. We can look at the heterogeneities within the electrodes, and with the fast focusing nowadays, what we might be able to do is just overall map the entire electrode with a non-focus beam, find the region of interest, and maybe focus on the greater detail. And this is just a summary for why CNM should be a choice for you if you're trying to do battery research, or overall any research. I don't want to go too much into details because Tao would be talking about it later during the day. And so with that, I would like to welcome all of you and invite my first speaker. Which is Tanvir Tamim, and he is a senior staff scientist, engineer, and group leader for the Energy Storage Technology Group within the Energy Storage and Electric Transportation Department at Idaho National Laboratory. He is leading a team of 12 researchers, and his focus is on advancing next generation high energy and power lithium-ion batteries, developing innovative methods and algorithms for failure modes, classification and quantification, estimating battery system life, and enhancing battery safety at both cell and system level. And with that, please welcome Tanvir, and let's wait for
just 1 minute.
transition. Switch slide.
City code. Yeah, it's good. Let me check. Thanks, Camilla, for the nice introduction. Thanks, Feng, for inviting me. It's an honor to be here. So today I'm going to talk about some of the research projects and the learnings, and so I'll also talk about some of the gaps we see where you guys could help filling the gaps. Let me see. This works too. This one? Oh. It's connected to this one. Oh, let me just use this one. Okay. Oh, all right. A little bit about Idaho National Lab. I'm from Idaho National Lab, as Camilla mentioned. So if you don't know much about that, there are some statistics. So this is the state of Idaho. This is Idaho National Lab. So unlike Argonne, it's not co-located in one space. You can see like we have about the whole lab is spread out in 890 square miles. Quite a bit of nice facilities. It's a nuclear lab, so you can see a lot of relevant research and activities there going on. Our last FY24's budget was more than $2 billion. Here's the staff number, and here are some of the other statistics. Right, so we have 5 directorates there looking at different types of energy research, and we are an applied lab. So we put a lot of focus on deployment at scale and see how different systems interact with each other. So by the way, I'm located in the in-town facility, that's Idaho Falls. So all the site facilities are like about like anywhere between 30 to 40 minutes drive. So a little bit about my department's research area. So we used to have this whole portfolio of research like 3 months ago as well. So where we started out from battery research all the way two mobility systems, but the department grew quite a bit, 50+ people, and the leadership thought that it would be a good idea to split it. So right now, the department, energy storage and electric transportation department, has two focus areas. One is the emerging battery technology research, and the other one is advanced battery systems research. Here in the emerging battery technology research, that's the group I lead, about 12 researchers right now. These are the area where we primarily focus on. So we do some materials research, but we do a lot of failure mode analysis. We test them, and I did try to identify different failure modes. So you can see we have been fortunate to have multiple programs, and these are all consortium type programs where we closely collaborate with Argonne, NREL, and some other national labs and universities. So this is kind of like the business portfolio, research portfolio. And here where you can see some alignment with this workshop where we are using different machine learning algorithms. The other sister group, they're one of their goals is to do benchmark testing for DOE. That group is dedicated for USABC type of testing, like pre-prototype battery testing for DOE. Yeah, and we have very nice test facilities there where you can test like point cell all the way up to like packs. So more than 1,200 channels we have. So yeah, primarily if you can look at the different programs, they're primarily funded by different DOE agencies, Vehicle Technologies Office, Office of Electricity, ARPA-E, and we also do some safety research where NHTSA funds those activities. So kind of shows how our research portfolio. So this is, you have a copy of this, right? So I've been reading it and I've been thinking, okay, what to include in my talk, and debated a little bit whether I should like just focus on one research study, or whether I bring in multiple research that we have done in the past couple of years and kind of highlight the gaps there. So I kind of settled down to the later option that, hey, let's keep it high level and show multiple research that I have done. So it's going to be a little bit high level, but I will try to identify the gaps we see where you guys could contribute going forward, and hopefully it will be beneficial to everybody. I am a mechanical engineer by training. I'm not a machine learning guy, but I do work with a lot of machine learning in my group. So if you look at different approaches to machine learning, you can see your database approach. You'll see a lot of research out there where they look at data, and the machine learning algorithm, they identify different aging modes and mechanism automatically. But one limitation is that you need a lot of data. You need a lot of good data to be able to do that. Machine learning algorithms can do most of the work if you can do the work, get the data. So it could be time series data, or like EIS data, or some other data, so you name it. Another approach is you do like kind of like physics, include the physics aspect to it. Like ideally, in an ideal world, you could have a model like a P2D model that will fully characterize a battery and provide you all the information you need at different aging states, right? And part of another approach is that you kind of use hybrid approach where you have some physics-based model and some data where that you use to get to different results, right? Yeah, advantage is high fidelity based on real physics, but the limitation is that the parameter identification could be a nightmare, right? To tune these batteries, and when you move from one battery system to another battery system, then you have to redo that quite a bit. So we are not following that approach as well. So what we follow is that we try to look at different signatures, electrochemical signatures that you can link with different aging modes and mechanisms, and we kind of then develop or bring in the machine learning into it so we can identify, classify, quantify aging modes and predict life. So that's been our approach, and for that we have been tracking RPT data, cycle by cycle data, and if you look at the data, then you can look at different data like capacity, voltage, current, power, resistance, Coulombic efficiency, incremental capacity analysis, end of charge voltage, discharge voltage, you name it. We pretty much look at pretty much all the signatures that can be associated with a known failure modes or mechanisms. Primarily looking at less than 5 or 6 TRL data, like battery level data. And our key focus is how can we quickly identify some kind of aging modes that's been going on in the battery, and then provide that feedback to the battery developers so that it can go to the next iteration, whatever change that needs to be made in the design. So this is kind of like, at this point, I'm gonna talk about some of the success stories that we have had, and at the same time limitation as well. So one of our early goal was okay, we have the data, and sometimes it takes quite a bit of time to age a cell. That means quite a bit of time before you know what's going on, and that's we wanted to shorten that time. We wanted to understand what's going in the battery without tearing open the battery as soon as possible. So the question was, how can we classify, quantify aging modes, different aging modes? So if you look at different aging modes, it could be multiple aging modes, LLR, loss of lithium inventory, loss of active material in the positive electrode, negative electrode. They could be lithiated state, delithiated state. Sometimes they could happen simultaneously, multiple aging modes. So I've been doing this like manually using classical approach, but it is very difficult, right? So I've been using EIS data, incremental capacity data, and track these changes and to be able to uniquely identify some aging modes. But it was difficult. You need that expert knowledge, and also it's time consuming, and you have to age the battery quite well before you confidently say that, hey, this aging mode is happening, or a pair of aging mode is happening, dominating aging. So we thought, okay, let's try to do a better job at it. Can we look at the RTT data, and more specifically DQDV data, and can you bring in some machine learning algorithm into it? So one thing we immediate kind of the approach is that, okay, now we need that data. How do we get that data? Like, we need a lot of test data. Initially, we didn't want to rely on a whole lot of data. So we thought, okay, it would be a good idea to use some coin cell data, like slow rate, charge, discharge data, and you feed that data into a model that will synthetically generate different data for different kinds of aging mode, different pairs of aging mode. So that can be done very quickly once you have that data. So we use a lot of synthetic data to supplement the DQDV analysis. So if you have that data for this particular pair of aging mode or a certain aging mode, you have the synthetic data for those known aging modes, then all the machine learning algorithm has to do is you look at the experimental test data and you compare the experimental DQDV curve with the synthetic DQDV curve. When there is a match, you say that, hey, these are the two dominating aging modes that's been happening in the battery. And we have had some good success that it was able to uniquely identify different aging modes, for example, LLI plus LM in the positive electrode or negative electrode. And we were able to quantify that as well, right? And we were able to do that like within 2 to 3 RPT tests, like within like 2 to 3 months of testing, right? And from there on, we were able to predict battery life as well. So and there also we use the same approach. Okay, if you use 100 cycles data, your accuracy may be a little less, but if you continually use more and more data, your prediction accuracy is going to be more. So the value here is that we were able to rapidly classify, quantify aging modes. We were able to provide that feedback to the battery developers, and they were able to do the next iteration, the changes. So that's one thing. Then we thought, okay, why not make it more faster? Why rely on sporadic RPT data that happens every month or every 15 days? Why not use cycle by cycle data? So we said, okay, let's look at that. So what we did, and this is joint activity with Andrel as well. What we did is we thought, okay, now if you look at cycle by cycle data, and now you have higher rate data. Now this coin cell data may not be relevant. What you need a good model to generate that synthetic data. So what NREL did, they used the P2D model and the EIS data to provide the synthetic data for DQDV analysis, and we use cycle-by-cycle data, and we have had some good success there as well. We were able to quickly classify, quantify, and predict battery life there as well. Here are some of the kind of like the comparisons there, and we have had experimental data as well, just for the sanity check. So cycle-by-cycle data was good. Then at this point, we are still talking about aging modes, right? We are not down to the aging mechanisms yet, but that would be more useful, right? What's the aging modes happening? So we thought, okay, let's look at some classification type of like decision tree type of model and try to get a little bit more information on that. So what we did, looking at cycle-by-cycle data, we were able to develop a decision tree type of model where we were able to, by just looking at operational data, we were able to distinguish lithium plating and non-lithium plating cells. So lithium plating happens at fast charging conditions, so which is not good for the cell. So we are able to do that, but just by looking at operational data, okay, this set of cells could be are lithium plating, and the other one is like normal aging, kind of like SEI dominant aging. And their mechanisms are quite different. If you have lithium plating, it has different aging mechanisms, and then if you have SEI, most surface dominated, is different. So that was another success story. Then we expanded that decision tree quite a bit. Where what we did beyond lithium plating, we were able to even classify loss of active material. Like more loss of active material and less loss of active material type of condition as well, just incorporating end of charge rest voltage data as well. These are some of the results here. So now, again, I'm saying that, okay, we're down to the point where we're comfortable with some decent data. We can classify and quantify aging modes, and we can do it very rapidly using time series data. It may need some work on the transfer learning. For example, if you can do it for NMC 532, can you do it for NMC 811? But it can be done. We think we can do it. But identifying the specific aging modes, that's the challenge we see. We see that it's difficult. It's difficult to get to that point. Specific aging modes means mechanisms means like, okay, this is kind of like you're looking at LAM. It could be delamination. It could be particle cracking, right? So sometimes it's very difficult to identify what aging mechanism is driving the aging mode. So I think that's where a lot of work can be done. You can see that in optical images. You can see that SEM images and tomography as well. And then also like, is it like this kind of aging modes, or is it like SEI or CEI type of like surface dominated aging mechanisms? So those are also going to be useful, and that's where the multimodal approach comes in. That hey, with time series data, you will have to use some of these different techniques to be able to tell what kind of aging mechanism is happening. And if you know that aging mechanism, then you can do something about it, right? So yeah. So what are the challenges? So you may require sophisticated characterizations, right? Could be time and resource intensive, and these are not time series data. How do you bring those into the machine learning framework and with the time series data so that you can, I mean, the machine learning can do the job and identify the aging mechanisms, right? So some innovation here is going to be very, very useful, and maybe it's the microscopy, maybe it's the synchrotron. So other limitation, what we see and sometimes we can't capture is heterogeneity, right? So this is lithium plating. I'm just using as an example. So and you can see lithium plating is happening in these cells, and we just see it's heterogeneous. And sometimes if you look at it, read about it, you'll see people say, throw at you different types of heterogeneity at different levels. But which one is really driving these heterogeneity, it's unclear. So some work there could be very beneficial. We have done some work with synchrotron X-ray here. I'm just showing that if you have lithium plating, you can see the lithium plating there, like using a synchrotron X-ray, and you can see they're basically 1-to-1. And under these cells were under similar conditions, but you see heterogeneous like aging. Like what is driving this heterogeneity? I think Camila participated in this work as well. Like you could have like heterogeneity in plane and through plane as well. For example, this one at high rates, you can see quite a bit of heterogeneity in terms of SOC. Now that could drive aging in a different way. How to better understand that? And also in through plane, you could have different types of aging, right? So I'm not going to go through it, but this kind of like synchrotron studies can provide a lot of information on what's going on in the aging mechanisms. So we got a lot of insightful information there. Another study I want to bring up is that these two cathodes, NMC811, they were under the same conditions, but this sample or this group aged faster than we did like XRD. Then we found that quite a bit of heterogeneity in this electrode. So what's predominantly causing this inhomogeneities? Can we do something about it? Can we identify these early on so that it doesn't drive the aging in a different way? Opportunities in materials engineering, we have studied like NMC 532, NMC 811. We have seen that the NMC 811, their grains were radially oriented, and that was beneficial for their better performance. So that's one of the learnings. Like if you can design a particle where your grains are predominantly radially oriented, you will have better performance out of them. So how did we discover that? So using EBSD, different tomographies, and combining machine learning to be able to discretize and group them together. So that kind of made it possible to be able to get to this kind of conclusions. You can do more. For example, like you can develop different models to be able to see, okay, what kind of design, how do you design the particles, right? You can see like the modeling is also suggesting the same thing, radially oriented. If you have grains, then its capacity fade is going to be less as compared to the other ones. So there are you can get a lot of guidance from there as well. But here, for example, one of the parts missing is that you don't see the surface interface modeling that effect. It's just basically chemomechanical model. So you can definitely expand it. Definitely is going to be more complex, and you would need more computational power. But that's something you can look at, and you can provide some feedback to enhance improve battery design or cell design. And the last thing I want to highlight is that, okay, you are looking at different data, different types of data, time series data, non-time series data, different specialized characterization data. How do you store those data? How do you provide those data to the machine learning researchers so that they can do their magic? Okay, so what we do, we have put up stand up a batterydata.energy.gov website funded by DOE, where we are releasing our internal data. Metadata is the key. Like, and you'd be amazed to see how much effort you have to put in to track and sometimes upload those metadata without making a mistake. So we do that. We are releasing data open source for machine learning researchers in a structured way so that they can use it. At the same time, you can always go in and upload your data there. It's accessible to everybody. So data curation, data is going to be key for more and more innovation. I think that's where I want to stop, but I want to just continue. I skipped this one because I thought I wouldn't have time, but we have also looked into EIS type of data. How can we develop some easy to interpret models so that can be linked with machine learning algorithm? Going forward, what we are doing, we're also looking into the multimodal approach, where I'm listing two projects, like enhanced validation for advanced battery supply chain and heavy duty vehicle optimized lithium-ion battery technology, 80 volts programs, where we are looking into some of these issues, where we are looking into the time series data, non-time series characterization data, how to combine them so that we can reduce the testing time. Because testing, it takes time, effort, and it's expensive. So one of our goals is how can we reduce the time and provide the information to the battery developers, upstream or downstreams, whoever is the end user, as soon as possible, so that we can accelerate the development life cycle. Okay, so I'm going to stop here and see if you guys have any questions for me. Yes.
Regarding when you're comparing your single data generated by the model with the experimental data, like did you all come up with like both these parameters are like responsible for like are dominant to get those aging modes?
Yeah.
And also did you all detect like by doing that fitting, did you all see like there were multiple solutions?
There could be multiple solutions, and that was one of the issues, that how can we uniquely identify different aging modes? On the parameter side, yes, there are some parameters who are more sensitive, and there are some parameters who are not more sensitive, right? You can come up, and if you go to the publication, you can find those information. But one of the issues is that can you identify a pair or like 3 aging modes? Most of the time, multiple aging modes happen at the same time. Can you, out of these 5 or 6 or different classification, can you uniquely identify 2 or 3 aging modes? Could be LAM in the positive electrode, negative electrode is positive electrode, what's then going on in the positive electrode, and then provide that feedback to the battery developers for the next iteration. Yeah, multiple solution. The innovation here is the uniqueness. And that's the most challenging part.
So thank you for the interesting talk. So I'm trying to understand better what the machine learning aspect is doing. Is it different than just optimizing the parameters in a model to fit your experimental data, or is it doing something beyond that?
So what a couple of things it's doing. First of all, it's providing the feedback to us. Okay, what kind of aging mode is happening, right? And it is providing that information like quickly. Quickly means like within, let's just say 1 month with 1 month of data, right? So within 1 month, if you have a certain design, battery design, if you cycle it with some cycling, if you know that, hey, my dominating aging modes is just loss of active material in the positive electrode, then you take that information and sometimes you do a little bit more investigation with advanced characterization, but it reduces a lot of guesswork from the entire process. Then what you do, you provide that information to the materials developers and electrode developers, whoever is making those cells, and then they can correct on it. Sometimes they can switch the material. Sometimes they can design the material in such a way that, let's just say, radially oriented versus randomly oriented grain. So those information we are primarily getting from the machine learning algorithms.
Hello, last year, the last question, please. This is sort of a curious question. Like in the case studies that did you observe any sort of unexpected correlations or casual insights that challenged any of the kind of traditional understandings of the fake battlefield or mechanisms, like any ahas or look at that?
We have multiple times, but I haven't had a slide for that. For example, we have seen how different materials age. For example, we were part of the Excel program. What we saw is that you have 532 versus 811. And our initial notion when we started the study is that, hey, 811 is not going to be good for fast charging. End of the day, we found that 811 was better suited for fast charging. Those kind of like, and also like how they age. Another insight we got is that if you 811 can take a lot of like particle cracking and you won't see any effect of it. But if you have the same comparable cracking in NMC 532, then you'll see a significant drop in performance. And so depending on the materials and a particular aging mechanisms, the effect could be significantly different. So yeah, well, I could name more, but because of time constraint, but yeah, it was part of the. Yeah, thank you very much. Yeah, let's see. Oh, yeah. I think we can use this one. Yeah. So the next by Sue Babinet. So like her to talk about again about machine learning AI for lifetime prediction. I will mention a few things. First of all, Sue is leading our grid storage at Argonne. Probably Argonne is known for battery for variety usage. One of them is grid storage, actually Sue is leading that efforts. Another thing I note that a couple years back, you heard of battery data initiative, and Sue leading on another one. You read the paper about the battery genome principle. So that's what out of this initiative. That's basically what I'm trying to talk about it. I think Sue will touch on that one also. I think, yeah. So this is very important. So my saying, one of the goal really was think about data, right? What do we utilize for this different reasoning? Another rule I want to point out for Sue this afternoon. 0D, there's a ton of discussion. It's more broad, get the people over from different background to think about what's next we could do. And that will be a few panelists come over to the front. We'll get like the index to bring up the ideas to have discussion. And I mentioned in my email, everybody, we are a very small group here, a small room. Always feel free to discuss. We just say bring up the questions, right? We have here those who have those in the battery community, and also if you look at our organizer, they are from APS, from CNM, the university. Really is good time for you to bring up what are the questions, what are we problems to address. I will stop here. I guess it's next to talk.
Thank you. Okay, we just have a couple more.
Yeah.
Oh,
yeah.
oh. We are at battery problems. Like this, so many batteries like start right now. Anyway, so I'm going to get started, and then there'll be an interruption. And I've got a timer here because I'm Italian and I tend to go on and on, but I'm going to try to control that. So first of all, thank you, and it's really wonderful to be here. I love to talk about this topic here, and what you're going to see in comparison to my esteemed colleague Timber, who I'm sitting next to, is he went through a bunch of stuff, but I'm going to dig in deep on one topic. Okay, that's the first thing. The second thing is at some point you're going to say, is anybody going to talk about APS or photons or anything? Not much in this talk. So you're going to get 30 minutes, a lot of 30 minutes of current voltage time and electrons running around. But in the end, it's all being set up to talk about how we want to have some APS data to make this even better. And so with no further ado, I'm going to try to do this without all the months. How do you say that? And anyway, so let's begin. My name is Sue Babinick. I am an electrochemist, which will be very obvious as the time goes on. I'm also the program lead for stationary storage at Access, which puts projects together across the way in Argonne National Lab. My co-authors are Noah Paulson, Logan Ward, Victor Venturi, Vignesh, who are in cells. And oops, here's my guys coming. And then also Joseph Cabal and CSE. Let's just take a second. And we can put this here, and this goes here. Let's put it. This is here. Can you, oops. I'll put it up here. Okay, this is
You want it. So what do you, inside of your color?
inside my color. Okay, is this good? Is this good? Does that work?
Do you mind if I change the screen sharing? We'll share your presenter.
Okay, just change away. Does this come to my time? I want an extra 5 minutes. Anyway, I can always talk while they're fixing that. So anyway, so that's this in, so not only is this not about, APS stuff, but it's gonna be a lot about electrochemistry, but it's also gonna be a lot about data science. Because the topic is rapid and accurate life prediction, which is a transformational capability. And when we're done, you're gonna know that I didn't invoke the word transformational lightly, because this really is a huge deal. And when you're gonna understand a certain amount of it, but what I also want you to understand is if you think that this can help you, come and talk to us. We can get you going to take this thing away. And we're very careful about the, okay, now what's happening? Does this work?
Yes.
We've got your presenter view online. We're trying to get it to be full screen.
Do you want to just do some more? I can hit another thing and keep talking while you help them, okay?
We might have to pull it down. Is that okay if we leave it like that?
Well, let's fix it for the people online. It's okay.
There's no one on.
We're recording.
So we're just recording?
Yeah.
Well, go ahead and fix it anyway. I'll put another slide up here. Anyway, that arrow is pointing to the fact that in order to get this life prediction problem solved, you have to have a collaboration between electrochemists and data scientists. I'm the one electrochemist with all these data scientists. They know so much more electrochemistry than I know data science. And they really are the ones that make this work. And I am so lucky to have the people whose name is by that arrow in a world where the picture is configured appropriately so that it can stand there. Anyway, before we get into it, I wanted to just give you one sort of commercial message about how well energy storage is doing. And I pulled this out of a Volta Foundation annual report. You can get this online. It's free. It's like 400 pages. If you ever need any data, are we okay? Okay, all right. We're okay. We're okay. And I got what, extra 15 minutes?
They left a corner on this one.
They did. Okay. Anyway, I just wanted to say it is broadly transformational. Look at the size of the markets that we have in this is last year. This is 1 year alone in transportation, 865 gigawatt hours. Okay, and everybody says EVs and transportation are the big deal, and that stationary is small. It's going to be like a tenth. But look at the number in stationary, which is the area I'm doing work in. When I came to Argonne, I had been working in EVs and I was in grid. It's like, yeah, it's important, but everybody is doing EV, you know. But no, this grid is becoming an ever more important part of the transformation of making a resilient grid and a robust America and all that other energy dominant stuff. But this is the thing that's got to happen. It's a big deal. And look at how big those numbers are. Okay. Now, that's all the good news. There's one big problem, which remains, and it's almost unimaginable, is that we have trouble predicting life to this day. Think of those hundreds of gigawatt hours. Think of all the money and all the time, and think about how the fact of this most unlikely problem that we have, which is we were really bad at it, and I'm going to tell you how we've gotten much better. So life prediction is obviously a key parameter everywhere. Discovering as you traverse the whole TRL range, it's a big deal. And here's like the situation as it was 3 or 4 months ago. Problem 1, it takes 12 to 18 months of testing to get 2,000 cycles to predict life. 2, cycle life is very sensitive to chemistry, cell design, details of use pattern. For example, the amount of energy that you use every time you cycle it. Three, simplistic character, and that's when we have the simplest characterization of life, which is just how many amp hours are left, or how much energy is left in it. And then four, as if that wasn't bad enough, real use and real life use patterns are often outside of the characterization protocols, which are miserable in themselves. So this is just like bad news upon bad news upon bad news. And I came to Argonne like 5 years ago, and we were fortunate enough to get an LDRD, which has got to be one of the single best investments they've ever had in LDRD, in my opinion. It's not biased. And this picture on the left-hand side, oh, they're back. Did you want to do more?
We don't see your full screen.
Oh, okay. Want to come and fix it? So that picture on the left is what we used in our LDRD proposals, and it got us the money that got started. That's where I met Noah. And Marius Scan was the one who introduced me to him and helped us get going. Marius said Noah's awesome, and it's true. So if you look at the initial capacity on the left and the extent of use on the bottom axis, I'm assuming, I'm going through a bunch of this because I'm assuming that you're not all battery experts. You can see that if we have one type of cell and we use it 3 different ways, we get 3 different outcomes. And if you look up there at the point of evaluation, that percent of capacity, that doesn't tell you what's going to happen because they're all the same. So having the capacity, knowing what the capacity is, tells you a simple state of what is the health, but it has absolutely no predictive value in it. So the state of the art was miserable. Health was defined as percent nominal capacity. It's a bad description. These things are very hard to get, and as a result, accuracy is a huge problem in an industry which is massive and needs it to get even better. So that's the bad news. Okay, now I'm going to just do this one quick little thing here because this is a science talk. I want to just talk about some of these layers of complexity. In design, everything contributes to that problem. Everything is literally important, okay? I always say it's like brain surgery, but nobody's going to die. It's that sensitive. Okay, you've got particles, electrolytes, foils, electrodes, separators. Thank you, Tanvir, for your wonderful talk before me. I'm so glad. Mechanistic failure modes. Battery degradation is complex. You can see because of the tremendous work that's gone on, there's a really excellent framework for understanding what those modes are and ways of characterizing it. And then on top of that, you have all this complexity, and then you've got there's these 2 big markets. I've got EV is obviously the one on the bottom, and I'm going to talk a little bit about the grid, which has a very high complexity, which makes life prediction even worse. So here we go. We're going to look at that again. I'm going to look at EV versus grid complexity, and I love saying this because when it comes to transportation, the economics require that you only use about 30% of the capacity every day. When you buy a car, an EV, one of the first things you say is not how much it costs, but also like, what is the range? And people want more and more range because they think of that big single event, which doesn't happen that often. But on a daily basis, they only use like 30% of it, okay? You go to the grid. The grid and electricity is a commodity. It only cares about how much things cost. In order to meet the economics, you don't have a prayer unless you use all of the capacity every time you use it. So as you can imagine, understanding life, you need to know exactly how much is in there. It makes it very difficult. Now, the complexity, that's just a picture of the grid, and I've got these question marks all over the place and dollar signs everywhere. Where you put a battery on the grid to solve what type of problem depends on the use case, the use profile, which will determine its lifetime, and it also depends on your value proposition. So bottom line, the demands of grid economics create a very high need for accurate understanding of lifetime versus use. And there's a lot of this that's going on. You can see how big that market is going. So the techniques that we have as electrochemists don't work, and we go, of course, to data-driven prediction, and this is where things get exciting and they get really good. The proposed approach, data-driven prediction, and I'm going to use 2 words a lot today. I'm going to use the words of diagnosis and prognosis. Diagnosis means what is the state of health of that battery, and prognosis means what is it going to do when I go use it, okay? Now, in data science, the use data that we're talking about first defines the advanced state of health And then the stressors that we're talking about in the uses will show you how this is going to change. And we're going to use the mechanisms that Tanver spoke about to talk about how those stressors, when you actually cycle it, convert into various use scenarios, various degradation modes. So here's just a simple diagram to get us warmed up. You've got a bunch of data. You need data. Capacity, energy, coulombic efficiency, resistance, LLI, LLAM. And we want to produce the future state of health, which is the prognosis. We know what the anticipated stressors are. And this is just a diagram that says, hey, we're going to use AI. Okay, we're going to use a lot of data to tell us first what it is. And we're going to use data from previous cycling of batteries to talk about how those stressors will change the advanced state of health. Now, let's talk for a minute about battery data. The battery data that we've been collecting in the past and the battery data that we're going to collect in the future are different in two ways. One is the battery data that we collected in the past was a mess. Think of like a closet where you jammed everything in it and you shut the door and everything's in there, but good luck. It was a mess. That was what all our files were. It was fine. We were in a different world, but we have machine files, we have spreadsheets, we have data sheets. We have to take that and we have to clean it up into a standard format, embedded metadata, high performance input output, and then we can go ahead and do the processing. Now, the person that was on the front of the last name in the first page, Joseph Cabal, when we had our first LDRD, it was 2 years. Joseph went and took a lot of the data that we had out of our camp facility. I'm going to talk about that. And he went in, and in 2 years, it took him 4 to 6 months to clean it up. And he had to put piece files together. And on the average, if you had like a megabyte worth of data, when you cleaned it up, you probably had 300,000 points. It's a mess. And that's the past. In the future, we're going to do a better job. We don't have to clean it up, but a lot of people are using historical data. So that's the quality of the data, and it was a mess. The second thing is we need a lot of data, and this is what Feng was referring to, the battery data genome. So in order to do data science, we obviously need a lot of data. And if you think about the fact that there's gigawatt hours in commercial products being sold, there's plenty of data that's out there, and it might be in a messy state. But the problem is that people don't want to share that data because it's considered to be either competitive or it's a question of national security. And this is a big barrier to the development of AI for life prediction for batteries, okay? We wrote a paper, there were several of us that wrote a paper talking about that problem and laying the groundwork for how do you go forward and solve that issue. It was called The Principles of the Battery Data Genome, BDG, and 3 of the people who are on this panel today were in it, and Tanvir, I'm proud to say, is one of the co-authors. But this was a proposal that we put together that said, how do you organize a community so that they can share data? They will want to share data, they will feel secure, and that it can be used efficiently. And this, I'm just going to expand on it a little bit more. This is not your usual APS sort of data thing. I'm just talking about, I'm giving you a story here. But this was a really big deal for data, the ecosystem and scaling in TRL. Here's the segments of the ecosystem, and here's the ecosystem participants. This goes across all different TRLs. It goes from discovery, which is this, in the ecosystem segments, it's the upper right-hand side. This is the materials and the electrode. This is the sort of data that we're getting here at the APS, okay? It goes from materials to cells to pouches and packs, and then those go into systems. We want to be able to ultimately connect all of this. So at the APS, we do a lot of materials work, and we also do some really nice looking at that in operando in the cells, but this is the system. Everywhere from professors at universities to people who are multinational corporations. One more little bit of data. So that's the type, we need data. People need to share the type of data, its sources and its scales. What we're going to talk about going forward is time series data, which is just current voltage time when you cycle it in and out, up and down and up and down. I wanted to let you know in advance that the cell data that we have provides all the training and validation information that we have. And it can be anything from a coin cell, like 100 milliamp hours, up to a commercial pack for iron phosphate on the grid, which is literally one pack. I mean, one cell is 300 amp hours. all of those have value, and all of that data can be used equally when we do our training. The training that we get to predict life is done at the cell level, and then we take it and we put it into the system level because that's where the applications are. And there's another whole aspect of that I'm not going to dwell on, but just understand that the basic feed and the basic insights are really developed at the cell level. Okay, so let's see. All right, I've got 15 minutes done. Let's actually talk about how we do it with current voltage time today, and then how we're going to take new information and ultimately integrate that into the AI tools that we have right now. So the way it's done today, it's current voltage time data is the key thing. You just take your your charge discharge curves, the raw materials, and you process those. This is out of any one of those cells of any size. From that, you generate features. Tanvir was going through that. You generate features, and from those, you do a selection process. You say which one of these features is most effective at predicting life, and that's when you get the life prediction. So this is the process: current voltage time, features, down select, and then do a prediction. Now I'm going to talk to you about the way the predictions went. The first predictions that we had, which I'm going to show you right here. This is a paper that we published. I think this was on one of your slides that Noah we published in 2022. In the old days, which was 3 years ago, life was defined as how many cycles does it take to get to 80% of capacity. So 80% of capacity, we know that that's a useless metric, but that's what we had. And we said how many cycles, and these cycles were routine, which is sort of irrelevant, but that's what we did. And that's what the data had. And we said, how can we predict how many cycles it takes? So we had data from our CAMP data set. CAMP is the facility over in 200 building where I am, where we make really good cells. Andy Jansen is the hero, who everybody knows. Andy makes these cells, and DOE pays for that, having a really great facility. They make cells and then they test cells. And from that, we were able to get 300 pouch cells, which had 6 different cathodes. The electrolytes were sort of the same mix, but they had different formulations. But this was a rich environment and different types of cathode chemistries. We did the process that I described before. From those, and thank you again, Joseph, for work 6 months to clean that up. Then we generated the physics-informed features, like, for example, we have DQDV, that's a fun one. And then we have resistance as a function of state of charge, and we've got open circuit voltage. We did this feature selection. And then we got our first publication, which is the numbers of cycles to 80% of capacity. So we have predicted versus experimental, and we were plus or minus, like I think it was 5% in this first study, which is really good. So that was really wonderful. We were still talking about percent of capacity, which is the original figure. And then we went forward, and we're going to talk about that. We're going to fast forward now to where we are today. So that's where we started. And I've got this thing, I'm calling it the evolution of life prediction capabilities. So if you go back 3 years to when there was that battery data genome paper, as surprising as it was, and as big as this industry is, there was not a lot of data science and life prediction that was out there. That year, it changed. There was almost like a step function in the number of papers that were written. It just took off. And that's when the battery data genome paper was written in 2022. I say it's at the precipice, but precipice in the good way for life prediction. And there were other very famous papers that went on in that time. But I want to capture for you how quickly things have evolved. Okay. Now, since then, there's been a rapid expansion in the capabilities of things that we've got going on. We went from cycles, how many cycles, to 80%, and you can do a good job predicting with few cycles, which was then. We're going to fast forward to where we are today, which is not just simple state of health as capacity, and it's not just cycles to 80%. We're going to show we can generate entire profile of whatever the property is versus cycle. And we're going to show you this. And if Noah was here, he'd be going like, oh my God, what is she going to say now? What we're going to show you is the proof of the concept. We've got it on the data sets that we have. needs to be proven on much more expansive data sets, but we actually have the proofs that we can do these things. And that's what I'm going to go into right now. So you've got this big need, and you've got data scientists, and you've got to start. And what is the last thing you need is you need funding. And we were very fortunate because there's a program called ROVI, which is Rapid Operational Validation Initiative, which is a DOE program for accurate life prediction in the grid field deployments that was put forward several years ago. It's funded by DOE 10 million from OE and 10 million from OSED. The target was 15 years investment grade performance based on 1 year of data, okay? And that seemed pretty daunting, but we said, sure, we'll go do that. And that was 2 years ago, and now it's like, yeah, we got it. So that's what we're going to show you. Let's see, there was something else I was going to say. I can't remember what it is. We were very fortunate to get this funding. Oh, I know what I was going to say. So any of those who want to write a perspective, do it. ROVI, when you go to the ROVI website, and if you talk to the OE managers, they say, this came out of the battery data genome paper. So we laid it out then, and I was socializing it like mad with Eric Shea and all those guys, but nonetheless, this came from that perspective, as well as other things going on in the ecosystem. So here's a little bit about the scope. We're looking not only, this is very grid focused, so we're looking at defining the use. It's more than just AI. It's creating the whole ecosystem around it. We have to have use cases. We have to have data requirements. We have to have a data hub, appropriate accelerated testing, and then AI tools. We're doing it for a whole bunch of different technologies. I'm only going to talk about lithium ion, and the team was 6 national labs. PNNL, Argonne, Idaho, NREL, Sandia, and Oak Ridge. Okay, so I'm going to restate the problem again very quickly in the terms of the grid. The first problem is field deployments have complex and non-uniform charge discharge profiles. Think of that picture with the grid, all those different things going on. It's very difficult to get representative data because utilities and other folks do not want to give it to you for a variety of reasons. We have to have a fully used battery, and life prediction is honed on cells, but the predictions extrapolate into systems. Now I'm going to tell you how we did that. And I'm going to say one of the key enabling innovations that we have is synthetic data. This is a lot of tremendous work that's done. Idaho does it, NREL does it, and NREL's done a tremendous job. But in order to do this, we had to use synthetic data. Okay, so I'm going to walk you through the technology flow. The data requirements, here's the data requirements, our use cases, industry outreach, reference performance tests. This one was spearheaded by Sandia, who did the lion's share that work. PNNL did the use cases, and Idaho did RPTs. I want to just mention briefly an RPT. It's an electrochemical characterization today. It's used to characterize this data help, but it's not a full charge discharge curves. And there can be short ones, which is a pulse, which is the best thing you can do, or they can be longer charge discharge. Did you have something?
I think his batteries just died again.
This one?
I checked just the other one.
I get it. Every time a battery dies, I get 5 more
Is
minutes.
it getting better?
That's because you used it too much.
No, actually, that's not fair. That's not fair.
Just this one. Just this one.
Choose this? Okay, let's just do this. Okay. All right, here we go. This,
I will just state it.
okay,
Go ahead.
okay.
Minutes.
All right, I'm running out of time. Okay, I just wanted to say RPTs are reference performance tests. They're all different kinds, short pulses, long, slow, full charge discharge in the absence of transport issues. They're known, it's not a new thing, but the world has not organized around what are the right ones to use. That's part of what happened here. In terms of technology flow, our data sources, since we had scarce lab data, and we're going to try to like bring everybody in. Okay. We have lab data, which we always have, field data, which we desire, but we don't have, and we got a ton of synthetic data, which is what I mentioned before. NREL is leading that. We have a data hub that comes out of Oak Ridge. They did the architecture, and the AI ML tools that is led by Argonne. And again, that's our hero, Noah, who is not here, but he'll be here later, as well as that wonderful team. And then we've got a digital twin, which is just a mixing box where all the information flows in a user-friendly way. One of the things we found along the way I wanted to mention, which is when you actually start interfacing directly with the outside world, is a simple thing, which is state estimation, is state of charge. They actually have trouble doing that in the field, okay? And I'm not gonna go into it, it was a surprise, but when you go out into the field and you go away from tiny little cells, you run into all kinds of problems that you never would have imagined. And I just wrote this down because this is still a stunning issue to me. All right, so I've got just like 4 minutes left. I'm gonna walk you through briefly how we're doing our AI. No, it would be better to do this. I'm gonna walk you through the steps, and then I'm gonna show you most importantly what the results are. So when you think of AI and batteries in life, you think of two things. You think of diagnosis, which is what is the state it is in right now? What is its state of health? And you think of prognosis, which is what is it going to do when I use it in the future? Okay. Diagnosis and prognosis, we had that in the world that was miserable, but we're upgrading it. The state of health is now including capacity and resistances, and the prognosis is going to include everything from like routine lab tests to complex uses. Now, if we look at this over here on this side, okay, right over here, first thing we do is we get a bunch of data. I took, this is literally a quote from Noah, take some chunk of data from past and optimize model parameters. So you take past data, you create the model, you do a prediction of all these different variables, then you go use it and you just iterate over and over and over again. You do a prognosis and you can take that data and you can both do a fresh prognosis, but you can also update the tool that you have with better parameters. And this goes forward and forward and forward. And that's what this process is. First tool, updated as you continue to use it, and it's all based on current voltage time. The feeds that you have are the stressors, which is another word for use case. Stressors means we've taken that use case and we've converted it into failure modes, which is what Tanver spoke of, and we call those the stressors, and then the metadata. I'm going to whip through this because we've had so many interruptions. There's two types of predictions that we do. One is online state estimation, which is an advanced state of health when we use streaming data. So your battery is out in the field and you've got a prediction on it and you look at what happened today. You take that, you update your prediction, and then you also update your tool to be a little bit sharper. We do this with common filtering. That's all I'm going to say on that. Oops, it's going the wrong way. We've also got offline state estimation, which is some very thorough, accurate state of health that when they're using Bayesian techniques. I'm not going to go into this either in the interest of time, but we use a lot of electrochemical basic modelings, for example. Equivalent circuit modeling, which is a very common tool that electrochemists use. And we also look at resistance versus a state of charge. Again, I'll whip through this in the interest of time. The mechanism that they used, excuse me, they use a transformer network, which is a very common tool in data science. The data sets that we used were the CAMP data set, which is shown down here. And also the iron phosphate data set, which was published by Berkeley right around that same time in 2022. So what I'm going to show you now are results of going from a prediction of the number of cycles to 80% of initial capacity to presenting you complex full profiles of various parameters versus charge with very little cycle life in it. Now, here's the best result that we have so far. We can predict for you, these plots over here are full, on the y-axis are various parameters, such as what is your resistance, what is your energy, what is your open circuit value, what is your capacity, versus the number of cycles. This is the entire profile, and this is created with only one cycle of input, right? So think of before, we said how many cycles to get out to 80%. That was the only thing. We've got the full profile here. And this was done for iron phosphate fast charge. We've also done it for the CAMP data set that is still in progress. You can see on the upper right-hand corner, the black curve is the experimental, the red is the prediction. It's really good for iron phosphate down here. It's not quite as good for CAMP. We're still working on that. And we're also looking on the simple thing that we did in the beginning, which is What happens if we use only one cycle to predict out to 80% capacity? You can see these things are moving along. The single most important thing is that it's one cycle to do the prediction. And I just wanted to take this and put this up there and show it to you. This is the plot that I had on the left side of the last slide. I really like to show it because it shows how incredible the predictive ability is. And again, remember, this is just one cycle of input, one cycle of context to do this entire profile. So it really works for this system here because we've trained it. Now these cycles are very regular. I have one more level of complexity I want to bring to you. Oops, I'm going too long. And that is what happens if you go from a routine cycle, like 100% charge, 0% discharge, 100% up and down, if you go to arbitrary cycles, which is what happens in real use. And the answer is here, is that we can do it. I'm going to go pretty fast because we don't have a lot of time. We've had a lot of interruptions. But I want to tell you that very recently we've had quite a nice breakthrough, which is we can take one cycle of context and we can take use profiles, which are arbitrary, which we generate, and that's what these green things are here. What is the depth of discharge? What is the temperature? And from that, we can actually predict what the outcome is going to be. And that's what this prediction is on the upper right-hand side. I've got it here. I've got it here again. Okay, they call that the ground truth. And it goes from 3 months out to 15 years. So we've gone from using 20 months to predict a single profile and a single use, which is limited, to now we have demonstrations that we can have one cycle in a random arbitrary profile and we can predict the outcome of it. And that's because we have really awesome synthetic data from NREL and some from other some other folks. So here's the summary. Okay, it's all been time series. Excellent time series foundation is established. We're poised for expansions, especially in grid use. Diagnosis went from simple to complex. Prognosis went from 12 to 20 months to being able to do it with one cycle. And that was a demonstration for a given model, given trained model. If you want to do it in your system, we need some more data. But it is demonstrated. The use cases for the grid there were none. Now there are many, and most importantly, you can program for anticipated uses where there was one previously. Now we can use synthetic data to generate arbitrary profiles and arbitrary data so that we can do these projections. Now that's quite a big leap. Okay, we need a lot of data, but here's the future. This is my last point. In the future, the data is not just time series. If we want to use electric chem, we can always go to EIS, HPPC. Here's something we all love in this room: microstructure, X-ray, NMR, and then computational work. Also, I'm not going to go into it, but there are also some other complexities in the grid. I think I'll leave it for that. I think there's been a tremendous amount of progress. We always need data, but we think we have enough that probably anybody here who's cycling batteries, we can give you a hand if you want to talk to us. We can get you started on something that can help you today. Thank you.
All right, so thanks to the organizer for this invitation. I absolutely love coming back to Oregon. I was a postdoc here almost 2 decades ago. And this is a very good opportunity, but I was going to say now for something completely different. I apologize to you because there is not going to be too much battery in this talk. I'm really going to talk about the molecular foundry because the organizers wanted me to. I joined the foundry end of March. One of the nicest things about the foundry is the view. You can see both the Bay Bridge and the Golden Gate Bridge from my office, which makes you wonder if I do any work at all. But it is one of the 5 nano centers, and it is adjacent to a multiple user facilities. We have the supercomputer, which is the NERSC. We have the materials project that probably most of you are familiar with, also located at Berkeley. We have our own light source, which is about to go through an upgrade. So we have a project to upgrade to the 4th generation. We also have a biocenter, which is the Genome Project. And we have the Energy Sciences Network. So we have users coming from all over the world, composed of 7 technical facilities, which I'm going to tell you a little bit about. So in this talk, even though I have spent most of my scientific career doing massive facilities, X-rays and neutrons, we're going to go back to the lab. Well, things that happen in a lab when you're making new material, synthesizing new material, characterizing them, and where are we heading for future, right? So things are changing, so I'm going to talk about a little bit of the data structure that we're trying to develop at the Foundry. So we have a strategy as well, and you can download and see what our 5-year strategic plan is. A nice little slide to tell you the breadth of work that goes on. We have over 1,000 users who show up from various different parts of the world, and of course within the country. We have a fair amount of engagement with the industry, mostly startup companies, because of our location. Bay Area, as you know, has a lot of startups, so they do come through our, mostly not through proprietary mechanism, but just regular science research where they publish their work. And also we have lots of different institutions that includes universities, national labs, and industry, just like the rest of the nanocenters. Okay, so we have, as I mentioned, we have actually 6 floors in this building. Each is a facility. We go from synthesis, which is organic, inorganic, and biological materials. We have characterization. So NCEM is the Electron Microscopy Center, which used to be its own center, but about a decade ago, they merged with the Foundry and became one big facility for users. We also have some imaging where we look at the data and try to analyze it. And we also have a fairly extensive clean room where we can do nanofabrication, mostly for research purposes and not commercial, not a giant one, but if you want to develop new types of processes for fabrication. And finally, of course, we have to hold all of that together with theory and digital and data infrastructure. This is primarily what I'm going to be talking about. That's Ed, who is the person who is doing our data infrastructure development. So as you heard in Andy Schwartz's talk on the first day, Department of Energy generally categorizes its sciences in 2 categories. One is fundamental science, which is the grand challenge type of work. And then we also have use-inspired science. So the battery science is primarily use-inspired science, but sometimes you also look back and see what are the big scientific questions that we want to solve. So this is essentially how we're organized. I'm not going to go through all of that, but that's the 4 different themes that the Molecular Foundry has identified as its central scientific strategy, and it all revolves around the physical and digital infrastructure. So one thing I think all of us are getting used to is more robots, right? In our labs, we have, instead of 100 graduate students making samples, we are now getting to a point where we have these robots that are making 100 samples. So these are some of the robotic synthesis that we have in both the organic and the inorganic facilities. And you'll see I have categorized them based on at what kind of condition they operated. So the Foundry originally, when like 2 decades ago, actually decided to go and look into these more robotic synthesis. So some of our robots are getting old, and we're in the process of replacing them with newer, because one thing you will know in this field, things are changing extremely rapidly. You can buy more efficient robots now for cheaper prices than you used to be able to do. So again, some of these characteristics. So if you're doing a heating of less than 350, you can use this system. For lower temperature systems, you can do this. This is mostly used for our biological combinatorial synthesis. There's a parallel screening mode here, which is going to make powder. I'm going to go a little bit more on this one, which is not just a robot that makes samples, but what we're trying to do is also integrate the characterization within it to make the sample and look at it simultaneously and build models around it. The other thing that we have a lot of is microscopy. And we have been hearing a lot about big data in the synchrotrons and the neutron sources. But these microscopes generate the amount of data they generate at a time scale. It is unbelievable. We can't actually store this data anymore. So one of the things that is happening right now is we are working on something called 4D camera distillery. And this is a DOE funded project that included several national labs who have these aberration corrected microscopes, which are generating 4 terabytes per minute, right? So if you're going to align a sample and have the right focusing and go to the right place, that is going to take a few minutes. And then if you have to store this data, then you would sit for half hour and not be able to do anything. So this project essentially said, well, media has figured out how not to store data on disk, but do streaming. So what actually this project does, it is streaming this data to NERSC and looking at it live and essentially developing all the algorithms that's necessary to use this mode to align your sample and collect data, which makes it much easier for users, especially if you have users who have never used these types of microscope. This is a really handy dandy tool that we can use. Okay, so this is a little cartoon of how we did things before in the lab. We have computers in an island. We have scientists making, or maybe in this case, robots making samples, and we have microscopes. They don't really talk to each other much, right? So you take one thing to the other island, and what we are really trying to do here is a data-driven workflow that we think is going to be the future of the Foundry. And that is essentially building the bridges between these specific islands that we are all used to using. So one of the things that, everybody's talking about, we wish we had saved the last 20 years worth of data because we would have had curated data to train this AI ML model. None of us thought to do it, right? But that doesn't mean we cannot do it going forward. So we are building this essentially. Now we're not doing it for a synchrotron or a neutron source. We're doing it for 100 on different types of tools that are sitting in the lab and trying to connect them as they make sense. So AI and ML obviously is going to come into play at some point in the workflow. But what we're also trying to do, we are a user facility at the end of the day. Sometimes all of us who have been at user facilities, we do this heroic experiment. Like Jordi just showed one. He looked at 200 particles, right? But then you look at Jordi's data and go, I want to do it too. That takes a lot of effort to put that whole infrastructure together so that it's easy for users to come and do it. So that is sort of the motivation behind it, is that we can turn heroic experiments into more user-friendly automated version of them. Remote access. This is another thing that started because of the pandemic. We had remote users, so we also have to figure out how to do it. But now there are certain cases where we don't have people traveling. They can do the remote data analysis using our high-performance computing. Obviously, you have to be able to find your data. You have to tag it in a way that it makes sense, so that there is a fair amount of infrastructure. Again, we heard you have to clean up the data first before you could use it. So this is the FAIR data where we want it to be findable, accessible, interoperable, and reusable. And then aggregate the data. There's all sorts of data coming from all sorts of sources. How do we capture all of that together? So this is the platform that is right now being developed. A platform that has essentially, it's a modular platform. So you have the whole idea is you cannot build a whole thing, but you can build modules for each of your equipment. And then hopefully, if you do it well, you can bring them together depending on how you're doing an experiment. So this is going to be essentially an additional tool for doing data acquisition, storage, visualization, and everything else. And the last one is very important again. If you're a user facility, and you also have to think about the generation of users. I remember when I first started at a user facility, most of the data people wanted to do command line because that's what the culture was. And all my users wanted to press a button. Okay, so that's something that you also have to keep in mind as you develop something. So we are trying to build it so that it is user friendly and modular. And so users can also build in modules as they go. So the platform is called the Crucible Data Platform. The data group is building this software infrastructure to connect the foundry instruments and scientists. And so here are some of the things that we're trying to do. I've already gone through most of it, but basically centralize the data storage. One thing that we have struggled with, and it's one of the things that Berkeley does, we have actually, everything is on Google, right? Now, I understand that becomes a little bit harder to work with other national labs. So this is something that, this is another reason why we're doing this modular thing, that it should not be dependent on the platform that you choose, but you can use the modules that make sense for your institution. So the ultimate goal here is to have something like this. We are just beginning. This is all cartoons right now. We're building the structure as we go. We have a few examples where it's kind of getting to work. So I think it's basically a new scientific pipeline. The ultimate goal we don't have a whole lot of resources, unlike the big X-ray neutron facilities. My data group is 2 people, okay? And I suspect the other nanocenters don't even have them. So what we're trying to do is to get like maybe all 5 nanocenters can come together, given we have similarities in what we do, to develop something like that as a platform so that people can come and use this platform. And also users can contribute to it, depending on how, because in a lab, things are always moving. You're bringing in new equipment, you're retiring old equipment, etc. Okay. And of course, we have a light source. We also want that interface to have some commonality, because we have a lot of users who come and synthesize the materials at the foundry and then go do their characterization at advanced light source. So we're also trying to collaborate with our counterparts at the light source. Again, very important, modular design. And hopefully, if we can all come up together, and we're hoping that it is expected there will be a push in AI, ML, data, etc. initiatives going forward. It is a priority for even our current administration. So if that comes through, perhaps that's a mode for all the nanocenters to come together to try to develop this together. Again, so as I said, we have microscopes primarily. We have this, and essentially we're building this model. And there is an example of this. This is actually a system that was recently purchased in the inorganic. The PI here, Carolyn Sutter-Fella, she is the early career scientist from the foundry. The DOE has an early career program, and her project is primarily to develop this. So what she's doing is, this is actually a thin film robot. So you're not making powder or single crystal, you're making thin films. She's working primarily on photovoltaics, the iodide, the methyl amine iodides and the perovskite halides. But the idea is, as you go through this synthesis, you can also combine some of the characterization here, and you can decide if you have a good film or not, right? So that is the infrastructure, and we are trying to use this system because it is generating a fair amount of data to train the network, so that when you make more, hopefully this training data set can actually also allow you to decide whether you have a good film or not. So this is just the start. This is the first sort of proof of principle of the format. I only have one of the experiments. So Brett Helms is actually one of the individuals at the foundry who is part of the Argonne battery hub. He's working on, he's going to be our next guinea pig. We're going to put all of his stuff, which is, as you can see, we have glove boxes like what Camilla was showing. We have channels where we're testing things. We're going to hopefully try to come up together. And I really only have, once we do this, then this comes afterwards, right? Any of you who are in the national lab system, you know that if you write a paper, I'm not going to go through it. I just wanted to show you that there are battery work going on at the foundry, and you can basically, the idea is to develop this data structure so that it makes life easier as we go into these giant combinatorial synthesis, because I think a lot of the development of future is going to come this way. And with that, I am going to thank you. And this is basically the foundry. We had a retreat at USS, oh gosh, I forget now. It's actually a ship that's docked in Alameda. So once a year we go out and get together and talk about science. And thank you for your attention.
You only have time for a couple of questions. We're sort of running away. Are there any questions?
Thanks for your talk, Panchina. I was wondering about your synthesis robots. Do you do anything like thermal, hydrothermal synthesis in them? And can someone drive one of these robots remotely as well?
Oh, I don't think we have remote driving of the robots offered for now, but I am not 100% sure about the thermal. I think there might be actually one, the one that Emory is developing. And we are in fact in the process of buying another one, which is called the Wanda. That might be able to do that, but you should talk to the folks. I can put you in touch if you're interested.
So I came in late. I apologize if you addressed this already, but in a big team that I am responsible for, we find that a challenge is getting the transfer from one team to another team right and sorting out what the format is. So I just wondered if you'd like to comment on that.
So actually, I think maybe my colleague here who is also trying to work with us. So we actually have started some collaboration with the Brookhaven Nano Center and the Argonne Nano Center. And the first block was basically just a platform. We're using Google Drive, Google everything, okay? So now Argonne is not gonna let them use Google, so we're still sorting, but do you wanna make a comment of how that has worked in terms of working?
No, I think the answer to that question is twofold. I think Argonne, we prefer to use Globus, so we're trying to work together to replace that as a part with Globus. But in terms of file format, yes, so it's a very challenging step. So or ambitious step. If you want to create a uniform file format for everyone, then the next challenge is the adoption rate, basically. So we're taking baby steps, but that's something that we have in mind as well.
Thank you. Thanks a lot. Let's thank Akshay again. Okay, so I'm going to talk. I was asked to talk a little bit about what opportunities there are here at the APS. So I wanted to talk about specifically techniques that we don't do at our beamline. I will mention them. But the first thing that I want to talk about was if you're doing battery research, you've got to use cells. And in my experience, it's really important to get the cell right so you can then get the data that you want. And there are typically a bunch of different cells. So we've used all of these. We've designed our own. So this is just a regular coin cell. This is punch a hole if you want to do XFs. You want to do diffraction. Sometimes you can do it through the cell if you're using high energy. That works well too. We've done that as well. There are issues with this. And obviously everybody knows that if you don't put enough pressure where you're doing your measurement, you won't see what you think you want to see. And so that is a little bit tricky. So this has worked. We also have done, there we go. I'm going to pass this over. There we go. We also have gone into a pouch cell. This works well. It works well in the lab. If you want to do diffraction in the lab, that works really well. It uses atmosphere to provide pressure. It's not great for gas permeability because if you're using polyethylene vacuum seal, it will degrade in time, and it'll degrade immediately in the beam. So you have to do more than that. You usually wrap it in Kapton as well. But this works well. We've used this on our beam line for doing XFs as well. We've also done some liquid cells or water-based cells, manganese oxide, nickel hydroxide, and so on. And it's very convenient to be able to use an SLA printer and design your own cell, build it, put windows on, and it works quite well. This is a cell that we had in line. We also have electrochemical cells for flow batteries. We've done work on flow batteries. This you can use for catalysis, you can use for battery work, lithium air batteries, for example, or air batteries. You need to do catalysis on the other side, so it's battery research. We designed this cell. We use it. You can see it's well worn. We've used it a lot of times. We've had to repair it, but we get really nice data off of it for fluorescence, primarily fluorescence. And of course, we've already talked about this. Jordy mentioned it. Camilla also has this, obviously. She's in charge of this, but the AMPIC cell is great. And we've used this a lot. I encourage everybody, if you're going to do experiments here at the APS, this is the first place you look, right? If you have to do fluorescence, then maybe you look at something else. But for anything that you want to do transmission, diffraction, XFs, whatever else, SACs, this is the place to come. It's a great design. You can stack them on your beam line and run them, and they run great. We've done some experiments on this. This was on our beam line we were doing 8 cells, XFs for a couple of days. We have specific problems sometimes with these cells, but that's our problem. And that is we use low energies. We have a lot of absorption. A lot of absorption makes it possible that the cell will fail in the location where you're looking. We see that happen all the time. And it's not the fault of the cell, it's the fault of our battery. And you have to take particular precautions for that. So all of these cells are important to use, and you can use them, but you also have to realize that they all have drawbacks, and you have to be carefully planning how to do your experiment when you do it. So let me show you a little bit of examples of what we've been able to get with the AMPIC cell. It's really works nicely. We've done PDF on sector 11 on the same batteries as we've done XFs. This is just one of the edges for one of the batteries that we did. And we studied this one through first initial, before we started charging all the way to the first lithiation for an anode. And this, of course, leads to the problem of having too much data. And how are you going to manage this? We have these nice pictures, but we haven't published this yet because it's taken a long time. And my former student is now gone. So I have to work on this. It'll take probably a couple more years to get it out. Unfortunately, it's really unfortunate. Okay, so let me move to the main part of the topic. And this is the talk. And this is the fact that we have a battery facility here at Argonne where we have, where we have that allows us to enable research in electrochemistry, and we have the capability of doing the cells. We have potentiostats and all glove boxes, and everything's available for the user. So this is really important, and it adds the capabilities that you might not otherwise have to bring. You might have to bring yourself all these things yourselves. I'm sorry, these are hiding. This is still hiding everything, so I don't know what I can do about that. No, can't move it. All right. So sector 12 is an example of the kind of beamline that you can use for XFs. You can use it for diffraction. You can use it for SACs, 12BM. These are data that were taken ex situ for a paper looking at sodium ion storage. That's what's hiding under here, sodium ion storage. Another experiment that was done at sector 12BM is for a zinc 2+ battery, it's an aqueous zinc ion battery. So again, this is XFs or Zanes in this particular case, Zanes. And then in situ XRD was also collected at sector 11 ID. So this is an example of a beamline that does one thing really well, right? It does XFs, does diffraction. That's not the main power of what we can do with the APSU, and I'll have an example of that as we go a little bit further. So this is another example. This is sector 27. This is some data that we collected at sector 27. This is nickel edge RICS. This is something that we found very useful. We've also done oxygen RICS at a different beamline elsewhere during the shutdown. But this allows us to see things like the back transfer of electrons from the oxygen back to the nickel. And this is something that happens in this particular material that we've made that prolongs the charge cycle and reduces the damage from oxygen redox. So this is something that we're about to send out for publication. But this RICS is really something that is useful in certain cases that you need to do. All right, so this microscopy group sent me a slide, and so I'm going to tell you what I really think is the most exciting part of what we can do at the APS. And unfortunately, this is hiding what says multimodal measurements, and this is the example. So we have multimodal approaches at the micro and nanometer scale, sector 2 and sector 19. This is the in situ nanoprobe, and this is one of the feature beamlines from the new APSU. And you can do lots of different things. So sector 2, you do at the micro scale, you can do XRF, Zanes, XRD, tomography, tachography, and laminography. And many of these techniques can be done simultaneously on samples, which is the real plus. Sector 19, everything but now nanoscale. So this is one of the, as I said, the feature beamline, and being able to do this work and do it in multimodal mode is really, really important. Because as you saw from the talk that the other talks that we've had before, if you bring a different sample in, it may be completely different. So if I take a sample and run XFs, and then I take a new sample and do PDF measurements, how do I know that it's exactly the same? But in this particular beamline, these two beamlines, you can do experiments on samples on the same sample, and that's a real plus. The kinds of experiments you can do is you can track individual particles. You can look at the charge discharge of different grains. Is it different grains in diffraction? And you can again, this is tracking different particles in the compositions, much like what Jordy was talking about. And then you can do identification of different chemical states. So these are just simple examples that I got from sector 27, and not 27, sector 2, the microscopy group. And pretty much that's what I wanted to do. I wanted to keep it short so we can get to the next talk, because we have like 15 minutes before the session is supposed to end. So thanks for your attention. Sorry if it took me a little bit too long to get started.